So this lesson is going to talk about direct and inverse variation. So the first couple examples we have here, we're looking at whether these situations are going to be direct variation or vary inversely. So if something varies directly, as one goes up, the other goes up as well, or if one goes down, the other will go down as well. Inverse means if one goes up, the other one will go down, and vice versa. So the hours that we work versus the pay that we get. Assuming that we're not on salary and that we're working an hourly job, the numbers of hours that I work, as they go up, our pay is also going to go up as well. So that would be a direct variation. The faster we drive versus our travel time. So the faster I drive, my speed's going to go up. The time it takes me to travel should go down. So since the speed is going up and the time is going down, they're the opposites, so that would be inverse. Length of the side of the square and its perimeter. We're actually going to look at this one a little bit more in a minute, but if the side of the square goes up, the perimeter also has to go up, so that's direct. Your GPA versus the hours you watch TV. Well, if you spend a whole lot of time watching TV, it would fall in theory that your GPA would go down because you're not spending enough time studying. So that would be inverse. Time for a block of ice to melt versus the temperature. Well, as the temperature outside goes up, the time it should take that block of ice to melt would go down. So that would be the opposite. And if the temperature was dropping, then we would assume that the time that the block should melt would increase. So that would be inverse because they're opposites. So now looking directly at direct variation, this is the equation that we can use for direct variation. You can also use k equals y divided by x, just dividing both sides by x here. So we would say that y varies directly with x, or that y is directly proportional to x. Both of those statements are equal and mean the same thing. And k is our constant of proportionality. Sometimes you'll hear it called the constant of variation, but again, same thing. So we're going to look at the perimeter of a square and why it's directly proportional to the length of a side. So each of these, since it's a square, are all going to be S. So if, let's say, my side length starts to go up, well, then my perimeter is also going to go up. So this is direct variation. Side length goes up, perimeter goes up. So the equation that we would use is our perimeter is equal to, well, I have four sides, so it would be 4s. So our constant of proportionality here is going to be 4. Now, if you think back to your time in Math 1, this is an example of a linear equation. So when we look at this pattern here in a moment, we should see that linear change in our table. So what I'm going to actually do here, for part C, is I'm going to look at my side length, and I'm just going to make a table to make life easier, versus my perimeter. And let's just look at 1, 2, 3, and 4 for side lengths. So if my side length is 1, my perimeter would be 4, because I'm using P equals 4S. My side length is 2. 4 times 2 makes 8. If my side length is 3, 4 times 3 gives me 12. And if my side length is 4, my perimeter should be 16. So what you'll notice, if you look at how these are changing, well, that's increasing by 4. This is increasing by 4. This is increasing by 4. That is my constant of proportionality. So when it's direct variation, if you made this a table, you should see your constant of proportionality being that constant increase here. Again, because this also represents a linear function, this is my constant rate of change as long as these are increasing by 1. So here, if we fill this out, our perimeter is directly proportional to the side length in our square, and our constant of proportionality was 4. So moving on to our next set of examples, now we're looking at some equations. So I'm going to use y equals kx. You can also think of k equals y over x. Oops, you can't see that. So right off the bat, I know that this one is no good because there's something added to it. And this one is not direct variation because 10 is being divided by x and not multiplied by x. So here I know for a fact this is direct variation because it looks exactly like this. So my k value would be 2. Here, if I divide by 4 on both sides, I would have y equals 1/4 x. That would be direct variation. My k value would just happen to be 1/4, which is okay. Just means it's not going to grow as fast as, let's say, our perimeter one with our constant of variation being 4. Here, if y is 10, x is 5. So if I wanted to find my constant, if y is 10, oops, x is 5, so then my constant would have to be 1/2. That's still okay in direct variation terms. Down here, I'm going to use this formula here and do y divided by x. And if that number is always the same, then I know it's direct variation. So 10 divided by 2, that would give me 5. 20 divided by 4 would give me 5. 30 divided by 6 would give me 5. So this is direct variation, and I know that k is equal to 5. Here, 1 divided by 1 is 1. 4 divided by 2 is 2. 9 divided by 3 is 3. No good. Not all the same number. Ten divided by 5 gives me 2. 20 divided by 10 gives me 2. And 30 divided by 15 gives me 2. That's good to go for direct, with our k value being 2. Last but not least, 5 divided by 1 is 5. 10 divided by 2 is 5. 15 divided by 3 is 5. That's also good to go with my k value being 5. So now if we're looking at graphs, if you have the formula y equals kx, we should see a linear pattern in our table, which means we should see a line on our graph, which would mean I would have 3 examples of direct, and that one is no good because these are all straight lines. Even though this one is decreasing, it would just be a negative variation constant, which is allowed, and it's okay. I know it's weird, but it's okay to have a negative variation constant. All right. Recognizing it from an equation, I would be looking for something in the form of y equals kx or k equals y divided by x. If I'm looking at a table, I'm either going to look for a, oops, if I could spell, constant rate of change, like looking for a linear pattern, or the same ratio of y to x. And for a graph, we want to find a linear function. So that's if it's direct. If it's inverse, we're actually going to see this function here. If you isolate k, then I would have k equals x times y. All right, so the time required to download a 4 megabyte music file is inversely proportional to the rate the data is transferred to the receiving computer. So I see that time is inverse to rate. This 4 megabyte is the thing that's going to remain the same. My 4 megabyte file is my constant because that will remain the same. And the time that it takes is what's going to be changing versus the rate. So how long is it going to take to download 4 megabyte file if my rate is 2.5 megabytes per minute? Well, I would take my 4 megabytes that I'm trying to download and divide it by the rate that I'm downloading. And that's going to tell me the amount of time that it will take that download to happen. So 4 divided by 2.5 gives me 1.6 minutes. Now, if my download rate or my transmission rate now drops to 0.8 megabytes, since my rate has gone down, I would expect the amount of time to go up. So I'm going to do 4 divided by 0.8, and that's going to tell me my time. I'm going to assume that it's going to be higher than 1.6, which it is. It's actually 5 minutes. All right, so expressing this in symbolic form, meaning as an equation, I would say that T is 4 divided by R. And I actually did this in a table as well. I did it sideways just because I didn't have enough room. And I looked at a rate of 1, a rate of 2, a rate of 3, and a rate of 4. So if my rate is 1 megabyte per minute, my time would be 4 minutes. If it's 2 megabytes per minute, 4 divided by 2 gives me 2. 4 divided by 3 would give me 1.3, and 4 divided by 4 would give me 1. So, since this is inverse, I need to look at the value of t times the value of r to determine if I have the same k value. Well, 4 times 1 is 4. 2 times 2 is 4. 3 times 1.3 rounds up to 4. This was a long repeating decimal, but it would give me 4. And 4 times 1 is going to give me 4. So since this is always 4, I know this represents inverse variation, and that value is my constant. So here I know that time in my download situation, time was inversely proportional to the rate, and that constant of proportionality was 4. So again, we're going to look at some equations. So I need k to be in the numerator and x to be in the denominator, or I could see y times x being equal to k. So that's no good because x is being divided by something. I could have also rewritten this as 1/2 x. So that actually is direct variation. That's no good because it's got something added to it. This one is okay. That one is okay. And that one is actually good as well, because if I multiply by x and divide by y, I get the exact same formula here. Or I could look at this and divide by y, so I would have x equals k divided by y, still valid. So here, this just so happens that all of my k values are 2. K is not always going to be 2 in inverse variation. It just so happened that these examples had a k value of 2. So going to look at some tables, I'm going to use this formula here. I'm going to multiply x and y together, and if I get the same value, then I know that that's my constant of proportionality, and these are inverse variation questions. So 12 times 1 is 12, 6 times 2 is 12, 4 times 3 is 12. So I know that my k value is 12, and yes, this is in fact inverse. Well, here 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. That's no good. Not inverse. All right, this one, 1 times 6, I'm going to work from the bottom up. 1 times 6 is 6, 2 times 12 is 24, so right off the bat, that's no good. Now here, 12 times 1/6, or 12 divided by 6, is 2. 8 times 1/4 is 2, and 4 times 1/2 is 2. So yes, that is inverse, and my k value is 2. Now, if you were going to look at this graphically, it would be this type of curve that's never going to cross x or y axes. And all 3 of these equations would be representing what's going on here. Again, it's never going to cross x or y, because if I divide something by 0, that's not valid. It would be undefined. And anything times 0 should be 0, not a value other than that. So again, that would not be true. So I'm never going to have these x or y intercepts. So here in my inverse variation, looking for an equation, I have y equals k divided by x, or k being equal to xy. From a table, if I multiply x times y, I should always get the same value. And from a graph, it's going to be something like this, never touching x and y. So just as a little cheat sheet or kind of rule to follow, if x and y are both increasing or both decreasing, I'm going to divide x by y to figure out what the variation constant would be. And if it's always the same answer, then it's direct. And what I'm doing is k equals y divided by x. That's what I'm using to try to find k. If x goes up and y goes down, or vice versa, then I'm going to do k equals x times y. And if I get the same answer every time, then it would be inverse variation. So there's a couple tables down here that we're going to look at. So here, x, these values are going up. These values for y are going down. So I need to multiply x times y to see if I always get the same number, which I do, and it's 200. So this would be inverse. Here, x is going up, y is also going up. So then this would be dividing these two. So I'm going to do 6 divided by 10, 9 divided by 15, 15 divided by 25, which I didn't actually do yet. So 6 divided by 10 would be 0.6. 9 divided by 15 is also 0.6. 15 divided by 25 is also 0.6. So this is direct because that division gives me the exact same number. Last but not least, these are going up. These are going down. So I'm going to multiply, which all of these happen to be 48. So that would be inverse. All right, finally, we have some word problems. So here, the speed of an object, so I'm going to label that S. It's directly proportional. Directly meaning I'm doing y equals k times x to the time, so I'm going to label that as t. So I have the speed being directly proportional to the time. So this is the thing I'm going to use to start to substitute. You'll notice they did not give us k, so that's what they expect us to find. So the speed is 14.7, so I'm going to substitute that for s. I don't know k, but I know that t is 1.5. So dividing by 1.5 here is going to tell me that k is 9.8. That's part one. Then they want me to find the speed after 4 seconds. So then I'm going to do 9.8 times 4, which tells me if an object has fallen for 4 seconds, its speed would be 39.2 meters per second. Last but not least, we have an inversely proportional relationship here. So we have that pressure. I'm actually going to relabel this when my document camera decides to unfreeze. I'm going to relabel this with P and with V, because that's how you would actually see it if you were in science class. So the pressure is inversely proportional to the volume. That means volume is going to be in my denominator. Now, again, they did not give us the constant of variation, but they gave us enough information to figure it out. So 25 psi is my pressure. I don't know my constant, and I know that the volume would be 400. So multiplying 25 by 400 tells me that my K value in this instance would be 10,000. Now I'm going to compress the volume to 125 cubic inches. So I don't know the pressure. And I know that my volume is 125. Dividing that gives me a pressure of 80 pounds per square inch.